Okay, so here we go for round 2, a moments revision. So I'm going to use questions which are from the book. So firstly, page 152, question 4. Why don't you try and draw a diagram for this, and then I'll come back and we'll work through it together. Okay? So hopefully yours looks a little bit like mine. Uniform beam means that the centre of mass is halfway along, so that'd be 2.5 meters along. Remember, if it's not uniform, then you need to work out where the centre of mass is. They'll normally tell you that. But when we're dealing with moments, we're dealing with twisting forces, aren't we? So this beam is being pulled in a clockwise and an anti-clockwise direction, but the fact it's in equilibrium means that those effects are cancelled out. And that means that anywhere along this beam, if we worked out the forces twisting it one way and the forces twisting it other way, they'd cancel each other out, they'd add up to 0. So you may remember we take moments about any point we want, but we have to be smart about the point we use. So I'm firstly going to take moments about B. And I'm going to say, right, I've got clockwise moments, that's things twisting it in a clockwise direction, and I've got anti-clockwise moments twisting it in the other direction. And because it's in equilibrium, they'll be the same. So why did I choose B? Well, that means at B, this tension in the rope has no effect because it is 0 distance from B. And you may remember that the moment, the twisting effect of a force, is that force times its distance from the point we're dealing with. And everything in this question is perpendicular, so we haven't got any angles to worry about yet. So the two forces involved are this force, which is going to be pulling it up, so that's a clockwise rotation, and the weight, which is pulling it down in an anti-clockwise direction. So clockwise, I've got whatever this tension is, times 4, and anti-clockwise, I've got 8g times 2.5, and so I know that the tension at C is just this divided by 4, so that's 2 lots of g rather than 8 lots of g, times 2.5, so that will be 49 newtons. Okay, and to work out the tension at B, well, I'm going to work out moments about another point. Now I know the tension at C, I could use A, but actually it makes a lot more sense to use C, because then I don't have to worry about the tension at C. So if I do moments about about C, this point here, so now the weight is actually pulling it clockwise, isn't it? So that's 8g times 1.5, and the tension at B is pulling it anti-clockwise, so that's tension in B times by 4. So the tension in B will be this divided by 4, so that's 2 lots of 9.8 times 1.5, and that's 29.4 newtons. Okay, let's have a look at the second part of this question. Okay, so in part B we're told that they add a mass to the beam, and the beam remains in equilibrium, but it's about to tilt anti-clockwise, that's this, got it wrong first time, about C. So it's still in equilibrium, but it's about to go ping like that. And you may remember this is a genius little step here saying it's about to tilt, because at the point of tilting there's no tension there. Now, where have they put the mass? Well, I reckon that if it's about to tilt in that direction, the mass is somewhere here, but it doesn't actually matter, does it? So I'm going to say, right, let's put the weight there, so that's 16g, and I'm going to take moments about C, so I'm actually going to call that distance x. I know it wants the distance from A, but in a minute I'm going to take moments from C, so it makes sense for me to call that my missing value. Okay, so remember there's no longer any force here because it's about to tilt, so the tension has gone. It's gone sort of, slack. So the only forces are this force here and this force here, if I take moments about C, so I don't have to worry about the tension there. So see if you can work out that distance there and therefore answer the question. So taking moments about C, I've got 8g times 1.5 going clockwise. It doesn't matter which way round you do those, does it? It doesn't have to be clockwise on the left. And then I've got 16g times x. The g's obviously cancel out, and you get x is 0.75. So that means that the distance from A is 0.25 meters, 25 centimeters. Okay? That's a pretty basic example, although it did involve the whole concept of tilting, which is a little bit more complicated. But let's look at one that involves angle. Okay, so same page, another question. Here we've got angles, forces at angles. And you may remember this adds a real unwanted complication. So in this situation, I don't know the length of the rod, and neither do I know this angle there. So it would make sense to take moments about B, so I haven't got to worry about that force at all. So the only two forces are this force, which is at this distance that we don't know, and this force, which is at an angle. So this force, the way we did it before, is to work out the distance, you had to work out the perpendicular distance between the pivot point, which is B and this point, and the line of action of the force. So it meant sort of extending the line of the force in either direction until it was at right angles to the force. And so this force would be 42 newtons multiplied by that distance there. Now at the time I did that, I remember a number of you saying you'd rather do it a different way. And now we've done resolving forces at angles, I think perhaps the other way is definitely the way to go in this situation. It may not always be. So here's how I suggest we solve this problem. It means we don't need to do this stuff anymore. So here's another copy of the question. I've put in some distances. Now x is what I'm trying to find, the length of the rod, and 13 is the distance that we do know. So instead of using 42 and multiplying by this perpendicular distance, what I'm going to do is I'm going to use the distance as it is, but I'm going to use the perpendicular component of that force. Okay, so that's 38, so that angle there is going to be 52. So this force in this direction is 42 cos 52, or 42 sine 38 if you prefer to do it that way. So the moment, if I'm taking moments about this point here, the moment of this force, I can do its perpendicular component to the beam multiplied by the distance, which I'm calling x, and that's perhaps a little bit easier. So taking moments about B, I've got the horizontal component of that force, the vertical component of that force multiplied by the distance, and I've got, going anti-clockwise, 11g multiplied by the distance, which is x take away 13. So go on, see if you can work out x. Okay, so hopefully you were okay with that. Just a bit of algebra really, when you've got the thing you're trying to find more than once, make sure you've got that on the same side, factorise and then divide. So I did that, divided by that, which gave me 17.1. Right, now so the second and third part of this question present us with a bit of a problem because we've got two missing values. We don't know this angle and we don't know this tension. So I can't just take moments about A because I've got two things I wouldn't know, T and alpha, and both of those would feature in that equation. So do you remember there was something else we could do with these moments questions, and that's resolve, good old-fashioned resolving. This thing is in equilibrium, so the forces going up will equal the forces going down. This is nothing to do with twisting, this is just the fact that it's not moving up or down. So I know that the two forces up, which is the horizontal component of that force and the, I keep doing it, the vertical component of that force and the vertical component of that force are going to equal 11g. So that's nothing to do with moment. There's no distance involved. That's just forces up must equal forces down. So I've got the component of this force, which we already said was 42 cos 52. This is another force going up. Now the trouble is I don't know that angle there, so I'm going to have to use sine alpha. So that's t sine alpha, and that's got to equal 11g. Now I can hear you saying, but that's still two missing values. I can't work out t and alpha from that equation. I know, but if I now combined it with the second equation, perhaps by now taking moments about A, I'd get simultaneous equations. And you could take moments about A. Some of you may have already done that. But actually, there's another thing we can do in this situation, which only makes sense when you've got forces at angles. I can resolve vertically. Because these strings have an effect in this direction as well as in this direction. And we're told the rod is in equilibrium, so it's not swaying backwards and forwards, it's not moving to the left, it's not moving to the right. So that means the vertical component of this force will equal the vertical component of this force. So I know that 42 cos 38 must equal t cos alpha. And I can combine those two equations to work out the things I'm after. You might, for example, decide to rewrite this equation as t sine alpha equals, and you've got t cos alpha equals, so you could do one divided by the other to give you tan alpha, or you might have another way. Anyway, we should now be able to answer part B and C with those two equations. If instead of doing this we'd taken moments about A, we would have been able to do the same. So I'm going to give you a moment to come up with a solution for that. Okay, so I rewrote the first equation as t sine theta on its own, so I took that away from both sides, and then I just did that divided by that, so that's that divided by that. Cancel out the t's, gives you tan alpha, so tan alpha equals all of that, so that's shift tan of all of that, got me 68.0, stored it, and then I just went back to this equation, and I now know what alpha is, so t is that divided by the cos of 68.000. I stored it and used that stored value. Okay, so when you are working at angles, you have the option of resolving or working out the perpendicular distance, and I think we're probably now at the stage where for most of us the resolving is easier. Let's move on to another example. Okay, we'll just do a very quick laminar question. You can read what you want into the fact that we're doing a very quick laminar question. Here, a laminar, if you remember, is something that has physical dimensions but zero width. It's basically like a thin piece of card. A, B, C, D means that its corners are labelled in that order, so I've gone this way. If it's hanging at A, it would look something like this. Now, because it's uniform, we assume its centre of mass acts at its centre. So I've sort of set it here, and so that's that weight there. And of course, that's the only force in this diagram. So what does that tell me about the way it hangs? Well, I hope you can agree that it tells me that I've drawn my diagram wrong, because at the moment, and this is where the perpendicular distance thing has to work, you still have to use it. If I work out the line of that force, that distance there is the distance I would use if I was calculating the moment of that force. So I would have to do 0.1 g times that distance there. You have to use the perpendicular distance in this case. But how can that be? Because there's no other moment to equal that out but we're told it's in equilibrium. So what that means is it must be hanging with the centre of mass directly underneath A. So it must be hanging like this. I'm going to draw that in first. So I've got my centre here, and this is A. So, oh dear, that's a dreadful drawing. Yeah. Right, I'm going to pause and come back. Right, that's better. So we've got to find the angle between AB and the horizontal. So they want this angle here. And so it's a little bit of trigonometry. So do you want to have a go? Remember, this is the centre of the lamina. This is 0.5 and that is 1. See if you can do a little bit of trigonometry to work out what's going on in that situation. Okay, half a dozen ways we could have done it. I looked at this little triangle here and worked out this angle, which together with that angle makes 90 degrees. So I called that one X. So this is halfway along, so that's 0.25. This is halfway down, which is 0.5. So I've got adjacent and opposite, so that's tan. And so X is shift tan of 2. And so that meant the angle that we were actually asked about was 90, take away that. So that gave me 26.6 rounded. Okay, that's a laminar question. Let's look at one final question, which is probably of the sort that will come up in the summer because of the way the wording is in the in that pre-release information. Okay, so do you remember the good old days when we didn't worry about friction, when everything was smooth? So if we had a ladder leaning up against a wall, you would have, the only forces in the situation would be the weight of the ladder, and if it was uniform, then that would be at the centre. You'd have a force pushing up from the ground, so that's perpendicular to the ground, not to the ladder. That's the reaction force there. You'd also have a force from the wall, so that, and that would be perpendicular to the wall. So those are the only forces. Now, if we are dealing with rough surfaces, then we've got friction to consider as well. And you have to think, okay, what does this ladder want to do? Well, really, this ladder wants to slip down the wall, doesn't it? And because friction opposes motion, that means that if it's rough, if the ground is rough, you've got a friction force going that way, opposing that motion. You've also got a friction force up here, opposing the motion of it sliding down the wall. And you do get questions with either this scenario where the ground is rough but the wall is smooth, so you've got friction here but no friction there, or vice versa. So there's 4 possible combinations, and so you've got to read the questions carefully. And here is such a question at the bottom here. So have a look and see if you can work out which of these 4 it is. See if you can draw the diagram. There's an extra force in this question as well, because we've got a cat. This is a story of peril. This cat is nearly at the top of the ladder, and the ladder is about to slide down. We're told it's in limiting equilibrium. That means that friction is at its maximum value and the ladder is about to go. So anyway, start with the diagram and then we'll come back and have a look at this question. Yeah, this is in the book. I'll look up the page now, but yeah, have a go at drawing the diagram first. Okay, so hopefully your diagram looks a little bit like mine. Actually, the letters for the reaction forces, you could call that R base or R floor and that R wall. I'm just using the convention they used in the textbook. This is on page 160, by the way. So there's 4 things I can do in this situation, really. I could take moments about the base of the ladder and moments about the top of the ladder. I mean, I could take moments about any point on the ladder, but that seems to be to make sense. And I could also resolve. Don't forget there's the resolving, which doesn't involve moments at all. So I could resolve vertically, and I could resolve horizontally. Now there's 3 things that I don't know, But of course, two of them are related, aren't they? F and R are related by mu, and it's mu that we're trying to work out. So, yeah, I'm going to encourage you to have a go at this. Now, the whole distance thing. So, if we want to take, well, I tell you what, I'm going to take moments about the base of the ladder. That way I can talk about the distance, can't I? So let's take moments about the base. So I'm taking moments about here. So that seems to make sense to me because that knocks out two forces. I don't need to worry about those two forces at all. Now, I've got three forces acting on that ladder, but none of them are perpendicular to the ladder. They're all at angles. So I've either got to use the way we used to do it, and so for this force work out the line of force, the perpendicular distance, so I've got to use that distance there when I work out that force, or I've got to resolve it into a perpendicular force. So we either drop perpendicular, drop a horizontal and work out that distance there, or we resolve these three forces so they are perpendicular to the ladder. Now I'm going to go for the resolving forces approach, but we should all get the same answer. So the first thing I encourage you to do is to work out the size of these angles. Now it seems to me they look a bit similar, but yeah, work out the size of those angles, then think, right, if I'm taking moments about the base, which of those forces are pulling the ladder clockwise and which are pulling it anti-clockwise? And see if you can complete that sentence or that that calculation. Pause and have a go at that. Sorry, not my finest diagram, but yeah, that's 65 because that's going to be 25 there, so that'll be 65. That's the same. That's not 65 though, is it? Because of alternate angles. This angle here is 65, so that's 25. So the component of this force perpendicular to the ladder is 4.5g cos 65 multiplied by the distance. It's a 5x metre long ladder, so that's multiplied by 2.5x. You've then got the perpendicular component of the weight of the cat, 1.3g cos 65 times by 4x, because that's 4x up the ladder, and those are the two clockwise moments, and then this component of this perpendicular to the ladder. We're doing it perpendicular to the ladder because it's the ladder that's being twisted. The wall isn't being twisted, the floor isn't being twisted, it's the ladder. So that's n cos 25 multiplied by 5x, and then because this is effectively one whole term, isn't it? And this is one whole term, and this is one whole term, so I can divide everything by x. So n cos 25 times 5 is equal to all of this. So n is equal to all of this divided by cos 25 times 5, which gives me that, which I've stored on my calculator. So okay, we've taken moments about the base. It's a lot of work, isn't it? A lot of work. So why don't you try resolving vertically and horizontally? We've got one of the things that we need, n, and we're trying to find mu, which requires us to find both r and f. So see if you can get somewhere with that, and maybe we can avoid having to take moments about the top. Okay, have a go. Okay, so resolving vertically, nothing to do with moments, just forces up, that's the only force going up, equals forces down, two forces going down, weight of the ladder, weight of the cat, so I can work out what r is. And resolving vertically, well, there are only two forces. This is the force of friction keeping it, resisting the temptation to slip away, and this is the reaction force from the wall. Those two forces have to be equal. The weight of the cat, the weight of the ladder, the reaction force are at right angles, so they have no effect at all. So that means that f equals n, and we calculated n in the previous answer, so I've got my exact value of that stored. So f equals mu r, so mu is previous answer divided by 56.84, which gives me my value of mu. Now, on the revision list for your exam, after half term, it mentions moments and it mentions friction. So if I was an examiner looking for questions on those topics, I'd be really pleased at finding this sort of question because, you know, it covers both of those things. On page 100, you'll find that example on page 160, and there's a few other examples around those pages. And then if you go over to page 162 and 163, you'll find a couple of other ladder-style examples. So you might want to have a look at those. Try making sure you can do another one of those. There are some other sorts of problems there, which we will cover. But I would suggest that you don't worry about those at the moment. Moments is a big topic, so there'll probably be a couple of moments questions on the assessment. Right, so that is me done for now. I hope you have a really nice half term. I will be on email if you need any help. Make sure you refer to the revision list so you're clear on what it is from statistics and what it is from mechanics that you need to revise. But I hope you managed to have a good break and that you're staying safe in this wind. Take care.